So good morning, good afternoon, and good evening. My name is Eileen Meenan. I'm a Market Development Manager at Keysight Technologies, which is formerly Agilent Technologies Electronics Measurements Group. I'm going to be the host today for today's webcast, which is entitled Techniques for Characterizing Spurious Signals. This is the 9th webcast in our very popular RF and microwave Back to Basics education series, so welcome. What I'd like to do first is explain to you a little bit about the WebEx system. So the WebEx Event Center allows you to sit back and have the navigation advance automatically. We'd like you to participate in our question and answer session, and you can do that by entering questions at any time during the presentation. Down on the lower right-hand corner, there is a chat window. Address your questions to all panelists by clicking on the pull-down menu. Our presenter today, Riyadh Saeed, and our question managers, Steve Sinelli and Pat Buell, will answer questions at the end of this presentation, but again, please feel free to enter them at any time. We do have a lot of people on the line today, so in the event that we don't get to all your questions, don't worry. If we run out of time, we will respond to them via email after the webcast. In addition, we also ask that you take a moment at the end to fill out a short feedback form that will appear when you close your WebEx session. So let's get started. Joining us today is Riyadh Saeed. Riyadh is a platform manager for Keysight's Microwave and Communications Division. He joined Keysight, formerly Agilent, in 2001, and during his 13 years with us, he has held positions in applications planning, sales development, and technical support. He has worked with customers developing and manufacturing RF and microwave components to full transceivers. This includes applications in aerospace defense, wireless communications, such as LTE and wireless LAN. Riyadh graduated with a bachelor's in mechatronic engineering from Chico State University. Also joining us today as question managers are RF and microwave application engineer Steve Sinelli and sales and technical support engineer Pat Buell. So thanks and welcome. Riyadh, I'm going to pass the floor over to you now.
Thank you, Eileen. Hello, everybody. Welcome. So today what I'd like to do is run through some basics. So the end goal is we want to do a review of the classic sweep time equation and reviewing the trade-off between dynamic range and sweep time. Next, we're going to cover review the basics of good spur searching strategy as a starting point and frame of reference for us to talk about the rest of the presentation. And then the last part, we're going to be reviewing some new technologies and techniques to help you accelerate your spur searching activities. And we'll go through each one of those in a high-level detail. Okay, and we have about 45 minutes, so we got to keep within that time constraint. So we'll have a lot of reference material later on if you want to dive deeper into any of these subjects. So first thing we'll do is review what is a spur and why we care about them. Like I said earlier, we're going to review the sweep time equation for spectrum analysis. We'll review the details of a good spur searching strategy at a high level, and we're going to translate that to an example. And then we have the four different areas we're going to review. New wideband ADC technology to enable spur searching, as well as new fast sweep capabilities, a new stepped FFT approach, and we're going to review noise subtraction and what's available in the latest preamp, external preamp capabilities. Some quick assumptions here. So I'm assuming that you have some basics, but we will be reviewing the sweep time equation. But res bandwidth filters, TOI, second order harmonics. I would expect you have some knowledge on that. When we talk about noise, usually referring to the DANL, the displayed average noise of the spectrum analyzer. Sometimes folks call it sensitivity, maybe the noise figure. And then when we talk about distortion, usually referring to harmonics, second, third order harmonics is typically what we're referring to. Okay. So one of the things that we want to start out with is what is a spur? So I looked it up in the Merriam Dictionary, Webster Dictionary. And if you read the definition by literal terms, it's not genuine, insincere, illegitimate of birth, or false or erroneous attribute. So if you think about this, from a spectrum perspective, this is actually a fairly relevant and true. A spur is generally anything inside of your spectrum that you have not designed into your device. So maybe in this case, you have a complex radar system. It's designed to transmit and receive at a particular frequency. Ideally, you would have designed it. You wanted just a single, let's say a single pulse, single tone, if you will, to be transmitted and received. But in reality, what you got was something more like this. And so in this case, you got harmonics maybe, you got clock spurs, you got all random noise, all sorts of signals that are being transmitted either over the air or received through your receive path. And as you can imagine, this creates a large amount of complexity for the RF designer. And so this is the challenge that you're proposed with in your everyday designs. So where do spurs come from? Well, they come from many, many places, as you know. Mixers are probably the biggest nightmare. Mixers, if you can imagine, will theoretically have infinite number of spurs. Okay. However, there are big ones. The second and third order harmonics are typically your biggest concern, but also you have their mixing products with their LO and IF inputs at the same time. So you have theoretically an infinite combination of spurs and where they may be. So this is probably your #1 challenge. But also if you have high frequency designs, maybe in military applications, you have multiplication stages. You have things like half rate and 3/4 rate, harmonics, subharmonics of those multipliers. Dividers create odd harmonics. You might have leakage from oscillators, LOs, VCOs. Maybe you have a frac end loop. Those generate their own spurs, okay? Amplifiers, DACs, maybe you have a DAC. You have repetitive quantization errors that show up as a spur. Maybe there's poor filtering. There's all sorts of things. Power supplies, you know, what will happen is your power supplies will get coupled onto your carrier. And so what you'll do is you'll have second, third order harmonics of your power supply riding on top of your carrier at low offsets, okay? All these things play into and create the spurs that might be generated by your device and all their mixing products, right? So you can see this gets very complicated very fast. And so a good design will try to minimize every one of these contributors to spurs at every step during the R&D cycle, all the way through to production. So why do we even care about spurs? Traditionally, or fundamentally, this gets back to usually receiver sensitivity, your link budget, the range of your device, and the quality of service that you're going to maintain during that link. So for example, in a radar scenario, maybe you have your transmitter here. And in this case, you're looking for a return signal. The return signal has a very small Doppler offset, very low amplitude. And your device happens to have a spur that rides right on top of that signal. In this situation, you will not be able to receive the return signal, and therefore you reduce the sensitivity of your radar. If you're talking about electronic warfare, that spur might get falsely identified as a target or a threat. And so in that situation, you also have issues. If you switch over to satellite, similar scenario, but in this case, you could think of it as in-channel receiver interference. So maybe you have a spurious signal that's inside your own chain, whether it's the transmit chain or the receive chain. In this case, you might be jamming your own receive chain as a result of a spur that's on your transmitter. Okay, you know, you might have a very tiny signal that your receiver has to decode and demodulate, and if you have a spur right next to it or near it, it can completely mask that wanted signal. In the case of, let's say, cellular, I'm using the example of an out-of-channel interference. So in this case, you might not be just polluting your own transceiver, but you could be polluting your neighbors. Okay, so let's say you're transmitting at one frequency, but your harmonics or spurs are in the adjacent band and masking the signal that they want to demodulate or decode. Obviously, regulatory requirements come into play. So in the US, you got the FCC that may regulate a certain harmonic or spur content. And you need to ensure that your device does not jam your neighbors in that situation, okay? And each one of these has various levels of sensitivity and how small they have to be depending on the use case. So this brings me back to spectrum analysis. So one of the first tools you usually go to look at and analyze your spurs is a spectrum analyzer. And if you're familiar with the basics of spectrum analysis, you basically have a very similar receive chain on your spectrum analyzer as it is your device under test. So there are spurs and harmonics that are generated by our own measuring device that you need to be aware of, and you also need to balance our own harmonics and distortion together with your device to find the optimum signal-to-noise ratio to measure your device cleanly and clearly and make sure you're not measuring the spectrum analyzer. And that has to be balanced with time. Now, in spectrum analysis, there's really three fundamental areas that you need to worry about. So there's distortion performance. That's the second and third order products from our own mixer. And then there's broadband noise floor, or the sensitivity of the system. So if your spurs are very small, very low level, 100 dBc or less, then the noise floor of the system will come into play. And you'll be able to actually see the signal is going to be your first problem. And then last, you have phase noise. All these will contribute to the dynamic range of your spectrum analyzer. For phase noise, traditionally, it's any narrow band. If you have very close frequency spacing between components, frequency components, that's when phase noise comes into play. For today's discussion, we'll be focusing mostly on 1 and 2. Now, the last sentence here is not to be dismissed. The above three factors must be optimized in combination with your DUT and measurement uncertainty. So the big deal here is measurement uncertainty. So having a good signal-noise ratio and having a good distortion ratio is going to be important for getting very accurate and repeatable results. And to give an example of this, let's say you have a large signal you want to review, but you need to increase the attenuation on the front end of the spectrum harmonic distortion from the spectrum analyzer. So in this case, you might add 10, 20, 30, 50 dB of attenuation. However, this adds more IF gain, which in turn degrades phase noise, or the broadband noise of the spectrum analyzer. And that's what we're showing over here. You can see there's 3 different attenuation levels. The one in purple above actually has a high degree of attenuation, and as you can see, there's a large amount of gain in that, and so you degrade the noise floor of the spectrum analyzer. The good news is you have a way of compensating for that, and one of the ways to do that is to reduce the resolution bandwidth filter of your spectrum analyzer. And by dropping the res bandwidth filter, you can actually drop the noise, and that's what we're showing here in this plot on the bottom right. So here we're going from a wide res bandwidth to a narrow res bandwidth, and we drop the floor by 10 dB. And you've got to do that in combination with your data sheets of your spectrum analyzer, and you have to balance those two. Now, the one thing that's missing from this graph here is the time equation, and we're going to cover that in just a minute. So there is a trade-off when you go with high attenuation and narrow res bandwidths. You actually end up trading off sweep time and sweep speed by a large factor. So before we get to the time equation, let's look at measurement uncertainties. Now, this is available in App Note 150 if you want to learn more details, but there's a couple graphs that I thought were very useful in that application note. And one's basically your uncertainty budget, and that's something you need to be planning for. And so on the left, we show basically it's almost like a signal-to-noise ratio, if you will, but for 2 sinusoids that are on top of each other. So if you have second and third order harmonics from your device, chances are those are going to fall right on top of the second and third order harmonics of the spectrum analyzer. And so you need to know the ratio that you're willing to tolerate for a given error budget. So if you want, let's say, in this first example, you have a distortion error budget of plus or minus 1 dB. If you read this chart on the bottom left, that means you have to have about an 18 dBc margin relative to the DUT input. So the harmonics from the spectrum analyzer have to be 18 dB better than your device as the input, okay? If you go talk about noise, here's a noise error budget on this bottom right corner graphic. In this example, if you're willing to tolerate plus or minus 0.3 dB of noise error, based on this graph, that will require a 5 dB basically signal-to-noise ratio relative to the noise, relative to your signal of interest, okay? When you combine those two distortion factors, or error budgets, you get a total error budget of a plus or minus 1.3 dB. Okay, so what you can see here is when you're designing your test for evaluating spurs, you need to keep in mind the signal-to-noise ratio and those sorts of things, because they could add a significant amount of added margin to get the accuracy and repeatability you need. Okay. So that is all good. Now, what I want to review here is the sweep time equation, because really what you end up having to do is you're under usually a schedule and a time constraint, a budget, and all these factors weigh into how much time you're going to spend on your design. And unfortunately, spurs are probably the biggest time sink that you could find out there in terms of trying to chase them down, find out where they are, and reduce them. And so you should be familiar with the sweep time equation. And here we have ST, which is sweep time, is equal to span over the res bandwidth. And what I want you to observe here is the res bandwidth is actually a squared term. Okay, so that means your sweep time is exponentially sensitive to your res bandwidth choice. Okay. And the reason for that, if you can imagine res bandwidth filter, it's a filter, and so the rise time of a filter is basically the inverse of its bandwidth. Okay, and in here we have a constant called K, which is proportional to the filtering, the res bandwidth filter shape, if you will, and other characteristics of that filter. Okay, and so that becomes very significant. So here in this graphic on the right here. On the top yellow graphic, we're showing a 300 kilohertz res bandwidth filter. Sweep time in this situation over a gigahertz span is about 1.7 milliseconds. Now, when you drop that by an order of magnitude to about 30 kilohertz res bandwidth, it jumps up to about 85 milliseconds. So, and the other trade-off here is when you have basically an order of magnitude drop in res bandwidth, you have the noise floor change. Okay, so in this situation, an order of magnitude dropped noise floor by 10 dB. That sounds well and good, but one thing to note is that a 10 dB delta in the res bandwidth actually resulted in a 50x increase in sweep time. So if you have an extremely wideband device, you can imagine the amount of time spent trying to trace down very small level spurs, especially in this example, we're looking at 100 dBc, could take a significant amount of effort and time. Okay. Now the other thing is this is great for continuous wave CW like spurs, but maybe your design has some sort of intermittent or walking spur. Maybe there's some frac end loop errors or other things causing a walking spur. So how do you trace those down? Well, for a swept-tuned spectrum analyzer, as you're sweeping, and we have the graphic here, as you're sweeping, your spurs might be showing up periodically. And here we have a graph in time and frequency. And as they randomly show up, the only way you're going to capture them is if the spur happens to show up right when the analyzer is sweeping through that frequency space in time. Okay, and so this brings us back to what's called the probability of intercept. Okay, and here we have an equation that describes the probability of intercept, and it's a function of basically your sweep time, the span, your res bandwidth, and how long your signal is present in that spectrum domain. Okay, and ideally you would want a probability of intercept of 1. That means you're going to capture it 100% of the time. But in reality, with swept spectrum analysis, there is a large gradient in terms of where that POI can be depending on your signal. Okay, so this is something to keep in mind, and we're going to cover some tools later on that will help you out to get to 100% POI and trade that off depending on your needs. Okay, so before you get started into your spur searching activity, a good rule of thumb is always to start with knowing your device. Okay, so you want to create a strategy to maximize your efficiency for all the reasons I listed above. Okay, so first stop, know where to look and what to look for. Okay, so in this case, you want to start with your block diagram. You want to look at all the contributors to spurs. You know you have a mixer, you know the fundamental frequency, the LL, the IF that it's operating at, you know your amplifiers, your synthesizer loops, anything else. You want to start with all your knowns and all your big transmitting spurs that could be present, such as from the mixer, okay, because you can find those quickly. And then if there's problems or issues in areas, you want to be able to keep track of those and monitor them as needed. But next you want to do is establish your required target levels. So you don't want to just start randomly looking at any and all spurs. You want to find out how low do you need to go. Do you care only about minus 50 dBc spurs, or does your device require minus 100 dBc? And that can make a huge impact in terms of how much time you're going to spend looking. And so you got to balance that with your schedule and time and the time you have available, okay? Also, you need to establish the type of spurs. Are you expecting just CW spurs? Are they moving? Are they harmonically related, or are they just random spurs from poor filtering or other issues in the device? Is it modulated, okay? Depending on the type of spur, you might choose a different tool or method to actually look for it or track it down or whatever you might be doing to reduce it. And then you got to keep production in mind. So you need, in R&D, you're usually looking for the cleanest, the widest dynamic range, the most sensitivity. In production, you got to balance that with the realities of test time, which become even more of a constraint, because now you have to incur the search time per device, whereas in R&D, you're just trying to do it during the early stages of development and then release it to production. And so you should have probably a two-tiered approach to that, but not always, okay? So usually the best approach is to partner with production early in the design phase, right? So usually you're tracking down spurs in development and you know where to look, where they are, and where there's problems, where there's design margin issues. So for example, if you designed a filter and you're right on the edge of the filter skirt, that'll have a tendency to have a large amount of variation. Your production teams should be aware of that and looking and checking for that particular spur at that offset. So being able to partner with production early in the design phase could really help focus on the problem areas of your design. And if designed well, you know, what you really want to do for production is design with enough margin in the development cycle so that you don't have to test to the same degree. So if your requirement's minus 100 dBc in the R&D design cycle, you might be targeting 120. That way you have enough margin where production doesn't have to look all the way down to minus 120. They could look at a minus 100 and have enough margin to pass the device. And like I said earlier, you want to keep production focused on problem areas, the variation in the product, as opposed to just something that's repeatable and maybe has a large amount of margin. And so that goes back, this goes to the last point here, is determine uncertainty budget. So you really want to set up your strategy such that you're testing with just enough margin to yield required results, because you don't want to stretch out your test time if you don't have to, because that wastes everyone's resources. So you want to test with just enough yield to get what you need. In production, that might translate, well, okay, if we have plenty of margin, maybe that ends up being that we have 100% pass rate. So you have large yields, you got high margins. So in that case, instead of doing 100% testing, you might choose to go to sampling of the device. And then you want to apply the appropriate tools for the spur that's needed, okay, whether it's swept analysis, maybe it's real-time analysis, which we'll cover later, or an FFT-based approach. Now here on the bottom, I have a block diagram of an example transmitter. You know, maybe in the design phase, in the early production, once you've got to a reasonably stable design, maybe you just want to look for in-band signals, okay? If you have pass-band filters, checking outside those bands might not be fruitful and waste a lot of time. So in production, you may just choose to look at in-band only, and assuming that all your filter banks are behaving in a proper manner and attenuating any spurs outside those filter skirts. So here's an example of where maybe you're targeting spurs about minus 100 dBc, and the maximum input from your device is minus 10 dBm. You got about a 40 dB of attenuation. You have a target error budget of about half a dB to a dB. This translates to a res bandwidth of 10 kilohertz. You're sweeping over the whole band of operation of your device, maybe from 10 megahertz to 18 gigahertz. In this situation, with this span and res bandwidth, your sweep time could end up being 5 minutes per sweep. In this case, you might want to test multiple modes of your DUT. So if you can imagine, spurs generated by your DUT could vary depending on the frequency that they're tuned to. So if you have frac N spurs, maybe every 10 megahertz or 5 megahertz that you tune your frac N could create a new spur. And so you might want to step across the full frequency range of operation, all the different bands, maybe even different power levels. And then you could have different modes of operation of your device. So all of a sudden, the number of permutations of configuration that your device will operate under could be maybe 500, 1,000 different test scenarios, okay? So imagine multiplying 5 minutes times 1,000 every time you change your mode of operation or your frequency, you have to rerun the sweep. So that translates to about 83 hours of test time to find those spurs. And then every time you repeat the design or make a significant change, you have to repeat that test time. So as you can see here, test time becomes a very significant portion, spur searching becomes a very significant portion of your test. And so today what I like to do is help you minimize that. And so to do that, I'm going to be introducing some new technologies and techniques that you could leverage to improve your efficiency, both in the early design phase and all the way through end production, okay? So to break that down, we're going to talk about large spurs, greater than -75 dBc, medium spurs, greater than 100 dBc, and small spurs, less than -100 dBc, as just some good starting points. Okay, so if we're talking about large spurs, there's new wideband high dynamic range digitization and processing that's available today. In this example, we have a new 510 megahertz capabilities. And so this is all done in, basically you got new ADCs and you have new ASICs and FPGA algorithms that could really accelerate some of your medium to high level spurs. And so then in the next few slides, what I'm going to be covering is available in our new UXA spectrum analyzer, okay? So if you want to find out more, that's the product you want to look for. In this case, this particular instrument has a brand new IF section. In this case, it has an instantaneous bandwidth of 510 megahertz with full IF processing. And so there's like 3 areas which we'll cover. There's dynamic range, and the ability to real-time process the signal, and it has excellent flatness for good measurement error budget management. So in this case, the real-time processing and the instantaneous bandwidth really lends itself to any type of intermittent spurs. So if you have any walking spurs, anything that's pulsed or modulated or is somehow unknown, maybe it's something you never planned for, this is an excellent tool for finding those signals. In this case, you're limited to dynamic range, and we'll talk about that more in a second. But some of the things you got to be asking yourself is, you know, if you think you're going to have intermittent spurs, you know, where is it going to be? Do you have any idea of how often it shows up? If you do, that can help you set up your test more appropriately. How large is the signal? Any bandwidth modulation types? The noise floor? The more you know that you think you know about the signal, the more tailored you can optimize this digital IF processing. Okay, so one of the advantages of a wideband IF is you don't have to sweep the analyzer. Okay, and so in this case, if you can imagine a swept LO, you're hoping as you sweep, you capture that intermittent information or that intermittent spur. But you can see here in this graphic, there's a lot of lost information. Everything that's in the brownish area is lost information. Anything that crosses the green line is captured, okay? So that's good for covering wide spans and good for the events that are stable in the frequency domain. It's only magnitude only, so you're not capturing vector information. But data, there's a lot of lost data. So basically, you're hoping that you capture the signal. In this case, applying the POI information we talked about above could help. But in this situation, there might be better tools. So one of them is to do a wideband capture if you're operating in band. Maybe you want to look at your in-band spurs. So you can park the spectrum analyzer, let's say at 18 gigahertz, your center frequency, or 2 gigahertz, and you could digitize the full 500 megahertz bandwidth. Okay. In this case, when you capture IQ data, you're still going to have missing information. So during the capture phase, it's continuous, but when you have to offload that data and store it, you basically stop capturing and you have a large amount of lost information. Okay, and so you still have a problem trying to find those elusive spurs. What we'd like to introduce to you today is the concept of real-time spectrum analysis. Now, this is not necessarily new, but the ability to do it over 500 megahertz of bandwidth is. And so the benefit of going to real-time spectrum analysis is everything is done in hardware, meaning FFTs and data captures are overlapping, so you have a large amount of overlapped FFTs, and as a result, you have zero gaps in your analysis. Okay, and so in that case, when you park it at your center frequency and monitor the spectrum, you're going to be able to capture everything with 100% of probability. Okay, but in this situation, you are limited to the IF bandwidth and the dynamic range of the ADC. And how is this all possible? It's all done with real-time ASICs. So you have a high-powered ADC coming in. And now you have real-time amplitude and flatness corrections for the receive front end of the spectrum analyzer. You have an FFT engine that's run in real time, as well as different views of that. So not only being able to process it, but also being able to visualize what you're seeing is going to be critical in this situation. So you have what we call density traces, spectrum traces, you got power versus time traces, and then you have ways of triggering off that information to either offload the data or display it on the processor, or on the display of the instrument. So a great R&D tool, but it could also be used in production if you choose to. All right, and so in this situation here, what we're showing is with real-time analysis, like I said before, you're parking the carrier at the center, and it's basically able to capture with 100% probability all the spurs that were transmitted in that channel, okay, gap-free. And so that's available on all of our new spectrum analyzers from Keysight, MXA, PXA, and UXA. And the great thing about the real-time analysis is you can capture signals as short as 2 nanoseconds, 2 to 5 nanoseconds in duration, okay? An example of the UXA, there's something called the probability of intercept for real-time analysis, okay? And that, POI in terms of real-time analysis is probably best described in terms of time as opposed to just probability. And so in this case, the 3.57 microseconds translates to 100% probability that you can see a signal with full amplitude accuracy. Now you could trade off that amplitude accuracy if you have a high signal-noise ratio and get down to about 2 nanoseconds, okay? And there is actually an equation for figuring this all out, and if you want to learn more about that, we have an application note, and it's available here. But you can see that the POI is really related to the window size for your FFT, the FFT windowing points, the bin size for your FFTs, and the degree of overlap that you have in these FFTs versus sample rate. So there's a lot that goes into this. I highly recommend you read the application note below to learn more. Now, that's how it works, but this is how you could be visualized on the screen of a spectrum analyzer. So in this case, we actually color code the signal as it comes into the spectrum analyzer, and depending on how long, it's coded in both frequency and time in terms of the color coding. So the cooler colors are infrequent, whereas the hotter colors in red are actually more frequent. Okay, and so for capturing really elusive signals that maybe only happen in a couple microseconds, you can quickly see them and visualize them with a large degree of persistence on the screen with the color coding. On here, we're showing a capture of 510 megahertz. Now, this is all great capturing wide bandwidth, but it really, if you're trying to do spur searching, you need to know what spurs are being generated by your device and which ones are being generated by the measuring device, in this case, the spectrum analyzer. And some of the advances in ADC technology allow us to see greater than -75 dBc spurious dynamic range over the full 500 megahertz of bandwidth. So that's never been available on off-the-shelf capabilities. And so this is a new tool that you can use to help you accelerate both the R&D bench as well as possibly some things in production. Okay, and you can have a large amount of confidence. Anything above -75 dBc will likely be your device and not the spectrum analyzer. Combine that with a large amount of very good flatness. Okay, so we have a lot of, basically the front ends of these analyzers have been designed to be extremely flat. That way we have minimal contribution to any error uncertainty calculations you may be having. So over our 500 megahertz of bandwidth right here, we're showing about 0.4 dB at this frequency. Typically you'll see about 0.7 dB of amplitude flatness. Okay, now that's great, but in most situations what you're limited to is the 500 megahertz of the spectrum analyzer. Let's say your device covers several gigahertz. What you could do is what we call stepped density method. So the previous plot we just showed was a density display. And what you could do is you can actually step sweep the spectrum analyzer with the real-time engine running in parallel. And so what this allows you to do is actually dwell the real-time spectrum analyzer at a particular frequency and then step to the next one in time. Now in this case you still lose information, however you're able to capture very elusive short events during that dwell time, and you'll be able to visualize them. And so in this example here what we're showing is that same approach. This is a stepped FFT or stepped real-time density plot. And here we're covering the full range of the spectrum analyzer from 10 megahertz in this situation all the way to 26.5 gigahertz with a fairly narrow res bandwidth filter. So we're able to see things below -75 dBc. Okay, and so this is a good tool to capture elusive signals. If it's a continuous CW tone, this is probably not the best way. You want to go probably to swept tune analysis. But for things that are hard to see or you don't know where they're at and they might be short and moving in duration, this is a very good tool to get you started. Now, what if you need spurs that are lower than -75 dBc? So there's something called fast sweep. This is a new capability available in our new spectrum analyzers, including the new UXA. And what this does is that it actually allows you to oversweep the spectrum analyzer and be able to perform sweeps 50 times faster than you have before. And this is available in our new UXA. Okay, so here we have your traditional swept tune analyzer. You have your sweep time equation. You've got your probability of intercept for elusive signals. In this case, as you sweep through, you're trying to capture those signals. And again, like I discussed earlier, you're going to be missing, if you happen to cross a frequency, a signal that's intermittent, you're only going to see it when the spectrum analyzer sweeps through it. Okay, so this presents a challenge. With the new fast sweep, what we're doing is we're taking the sweep time equation and we're modifying the K value, which is really the parameter of the filter, of the res bandwidth filter, and we're modifying it with an ASIC that allows us to sweep significantly faster. Okay, and so now what you could do, because you have a faster sweep rate, you have a greater probability of intercept during that sweep process. Okay. Not only that, if you're looking to improve your sweep time for just continuous wave signals. In this case, let's say you're doing your traditional method. You had a 20 kilohertz res bandwidth filter, and you're sweeping over the full range of the spectrum analyzer all the way to 26 gigahertz, for example. That might have taken about 79, 78, 80 seconds in the previous method. With the new fast sweep capability, you can improve that by over 50 times. Okay, so the same setup will now be accelerated to about 1.5 seconds. So it's a huge improvement over previous techniques. Okay. Now, to review some background on how this is all possible, one of the problems you have with swept tune spectrum analysis, you have a limited rise time in the res bandwidth filter, and so you can only go as fast as physics will let you. And so in this case, what happens is when you start sweeping too fast, the res bandwidth filter cannot react fast enough to that because of the filtering. Okay, so what ends up happening is you get three errors. You get an amplitude error, and you get a bandwidth spreading of the signal. It looks wider than it actually is, and you get a net frequency shift in the signal. So this actually ends up being a very complex error, meaning there's both phase and amplitude error happening at the same time. The good news is with leveraging modern DSP, we can actually correct for both the amplitude and basically bandwidth and frequency shift by applying some inversed functions in the digital domain to correct for the error. And so the net result in this case is you get about a greater than 10x improvement in sweep speed. Now it depends on the mode of operation of the spectrum analyzer. So in this case, if you're in FFT mode, there is no improvement in speed, but if you're in swept mode of operation, it's usually greater than 10x. In the example before, it was up to 50x improvement. And here we have an example over a gigahertz span, okay? So depending on your use case, it could be a huge delta in sweep speed improvement. And so that gives you a lot of options in terms of trying to optimize your time versus dynamic range of your test. Not only that, because you have the added flexibility now to improve your time, you can actually improve repeatability. So going back to your uncertainty budget, if you can improve the repeatability of your test, that might actually deliver a higher yield. So if you hold the sweep time constant while using, for example, a narrow res bandwidth filter, because maybe sweep time is not a concern. Maybe you want to keep the sweep time about the same, but you want to narrow the res bandwidth filter. By narrowing the res bandwidth filter, you effectively are increasing the signal to noise ratio of your measurement. And if you're increasing the signal noise ratio, what ends up happening is you increase the stability of the measurement. And so what we're showing here is you can actually get a much higher degree of repeatability if you hold sweep time constant and reduce your res bandwidth filter. Okay, and the good news is you don't have to take a hit in sweep time. In most cases, it'll be either faster or the same with a higher degree of repeatability, or vice versa. You can flip it. So in summary, fast sweep technology allows you to do four things. You can dramatically reduce sweep times for CW spur searches. You can improve your measurement throughput while maintaining accuracy. You can improve your repeatability. And it also gives you a lot more flexibility to balance the two. Time, repeatability, and accuracy can all be balanced in a much easier way without taking a significant hit on time. So very powerful, and this is available on all our new X-series spectrum analyzers, including the new EXA. So let us know if you need any more details on that. Now the next approach is what we call stepped FFT. So in the previous block diagram, we were talking about a traditional pre-selected spectrum analysis. Now there's other approaches, and one of them is not pre-selected spectrum analysis, but basically FFT based. And there are trade-offs in this case. Because you have no pre-selection, you're going to have all the mixing products from the mixer coming into the measurement. But now there's smarter techniques to actually manage that and still deliver excellent results. And so this new capability that I'm talking about is available in our PXI E vector signal analyzer, or in this case, the M9393A. So if you want to learn more, please let us know. In this approach, what we're doing is, if you can imagine, we have 160 megahertz of bandwidth in this product, and what we do is we step it across the frequency range. So you could step it across a full 27 gigahertz range of operation. And basically, what we're doing is we're taking advantage of very fast processing capabilities in new CPUs. And what we're doing is all the FFTs are concatenated together to create the full span. And we're using high-speed LOs and digitizers in a list mode to enable fast stepping across the span. And then we stitch these all together. Now this is all well and good, and if you got a fast processor and you got a good PCI Express backplane, things can happen very quickly. Now it is solid state, so you do have a small hit in dynamic range with some of our other spectrum analyzers, but you can balance speed with dynamic range, and in some situations it could end up being faster or it could end up being slower, depends on your use case. But for production, it might hit just the right spot. Now, one of the big trade-offs here is there's no pre-selection in the spectrum analyzer. So what we're doing is actually what we call digital image rejection. And the concept is what we call high-low side mixing. And what you're doing is you're really looking for the real image, which is the real IF, or the real transmission band of interest that you're looking for. And because the spectrum analyzer can tune so rapidly, what you could do is actually take 2 or 3 sweeps in what would have taken, a longer time in previous techniques, and you can make actually 2 or 3 measurements and determine which spurs are generated by you and which spurs are generated by the spectrum analyzer. Okay, and so what we do is we do a low side response, we do a high side response, we apply a max hold technique, and then a min hold, and that effectively does image rejection of the harmonics of our mixer. Now, it does take 2 acquisitions, but again, because you have fast processing speed and everything else, in many cases that's a very insignificant part of the measurement. Now, there's other things we do. So this works great for CW-like signals. As you get modulated or pulsed signals, you got to be worried about getting confused between what a real spur is and what it's not. And there's other techniques such as IF dithering and the max hold functionality that I described earlier. Now there's quite a bit that goes into this. If you want to learn more about this, there's a dedicated application note I have at the bottom here that goes into greater detail on how this actually happens. But the net result is you have extremely fast tuning speed. You maintain excellent amplitude accuracy, so you remove some of the hardware components such as the pre-selector on the front end, which could add some uncertainty. And then you got the compact physical size. So we have the PXI form factor. So for production, this could be a good fit. And here we're showing a graphic illustrating a 2 gigahertz wide FM chirp through an ARB. And so you got the chirp itself. You have also the alias product from the ARB, and then you got the clock. And in this case, this particular spectrum analyzer is able to see all these things and eliminate any of the mixing products from the spectrum analyzer and do it in a fairly rapid manner. As an example here, we're showing with a 10 kilohertz res bandwidth over 27 gigahertz span, we can sweep that in less than a second. Okay. And this could achieve over 300 gigahertz per second sweep speed. So whether you're looking for the maximum dynamic range or in this case the maximum speed, you have many tools to choose from, and this is one of them. And so again, a lot of this has to do with very fast LO. It is a solid state design, geared for production, so it eliminates all the mechanical attenuation, everything else that might wear out in production, so you could do this repeatedly over and over again. And it has a list mode, so it makes it extremely fast. And we have a very high power processor to process all these sweeps, so everything's geared for speed. And so if you're willing to trade off a little bit of absolute receiver sensitivity of the spectrum analyzer, this could be a good alternative to, let's say, a UXA or PXA high-end spectrum analysis. Okay. So moving on, I have a couple more areas to cover before we wrap up here. Now, let's say you need spurs lower than 100 dBc, and so you need a large amount of margin. There's a couple of different approaches. There's preamps and noise subtraction. The first thing I want to talk about is noise subtraction. All of our spectrum analyzers have the ability for noise subtraction. Okay. So it's a good way to accurately measure signals close to the noise floor. So if you're getting close to the noise floor of the spectrum analyzer, turning on noise subtraction is always a good thing. The trade-off is time. Typically, you want to have more averaging when you have noise floor subtraction because there's a higher degree of variability. But that's only needed if you're close to the noise floor. Now, if you have enough carry to noise ratio, that might not be necessary. So you'll have to balance the two. Now, in terms of hardware differences that are available to you, for example, our PXI sources are usually software-driven noise floor corrections, whereas in our integrated instruments, it's all done through real-time ASICs, and so there are speed differences in those situations. So you'll have to decide what's going to work better for you. Okay. And if you want to learn more about noise subtraction and how that is achieved, we do have app notes that talk about that as well, okay? But as you can see here, by adding noise subtraction, the graphic here is showing you actually can reduce your noise uncertainty. So you have a large scale signal here dropping all the way down into the noise floor. By turning on noise correction, you essentially have improved the accuracy. So the high signals had really little to no error, but the low signals had almost 3 dB of error, and you're able to recover that by turning on noise floor corrections. Okay. Now the other option to you is instead of turning on noise floor corrections, or in combination with, you can turn on an internal preamp or an external preamp. What's new, which I would like to highlight today, is our new external preamps. And what's nice about these external preamps is you can actually extend the dynamic range of not only your existing spectrum analyzers, but even some of the newer ones as well. In this case, these new USB preamps are pre-calibrated. And so basically you plug them in, and it'll load up all the calibration and correction factors for that particular USB power sensor. And you can use that sensor as a full front end of the spectrum analyzer, like it's integrated inside the instrument. Okay, fully calibrated, meaning you could do amplitude measurements, everything, like it's a part of the spectrum analyzer. So it makes it really easy, plug and play. But the big bonus here is you get up to 2 times improvement in the noise figure of the spectrum analyzer, which can help you not only improve your absolute downhole noise floor, but also improve your measurement uncertainties. And so that's a nice new tool that wasn't available previously. Okay, so I'm going to wrap up today. So in summary, you want to start with a good spur searching strategy based on the signals that you plan to see. And then you want to balance it with the sweep time considerations. And once you've processed all that, you want to look at all the new tools you have available to you. So in this case, with the new digital IF processing that are available to you now today, you have several choices. You got the RealTime with step density capabilities to capture repetitive or non-CW-like signals over large bandwidths. You have just the fixed tune real-time spectrum analysis if you want to just measure in-band, especially for signals that are very infrequent. You have pre-selected fast sweep capabilities where both speed and absolute dynamic range are extreme high priorities. If you want to balance dynamic range, but in favor of speed and maybe form factor and density, we have new stitched FFT capabilities with digital image and spur rejection. Again, a new capability never before available. So to accelerate both your production needs and fit in a small footprint. And last but not least, we have noise floor corrections and USB preamps to extend the dynamic range of the whole system and improve either your measurement uncertainties or allow you to balance the sweep time equation depending on your needs. And so with that, I think we're out of time, and so I'd like to open up the questions side of this presentation.
Great, thanks, Riyadh. So once again, before we get started, Keysight does hold many free webcasts throughout the year, so please, if you can at the end, take a couple of minutes and complete the feedback form. It does help us give you the best quality presentation, so we do really appreciate it. So we'll get started with the question and answers. The first one, we've got our question manager, Pat, on the line. Apparently we were made aware there was a typo on slide number 14, so Pat, if you want to just comment on that really quickly, that would be great.
Yeah, thanks, Eileen. Yeah, the point was made that the numbers didn't match up that were shown on that slide, and that is correct. The example given would have resulted with a noise floor even if the analyzer was capable of measuring at KTB. The effective noise floor for the input attenuation setting and the resolution bandwidth setting would have been a few dB higher than the spur level that needed to be measured. That was an error on that slide, and it'll be corrected before the final slides go out to you folks.
Great, thanks, Pat. Okay, so we have a first question here. How do we determine K for our spectrum analyzer?
I'm sorry,
okay, that's
how do we determine K for our spectrum analyzer? That's
kind of an internal number that we use. There's a lot of variables that go into K. A lot of them have to do with some of our FFT processing capabilities and capabilities of our ASICs, different levels in there. But usually we don't publish that type of information. But one of them is, like I described earlier in the fast sweep approach, we do basically a correction that applies amplitude and phase correction to the signal as it gets processed through the IF chain in real time. But that's all I can comment today.
Thanks, Riyadh. So on the note of fast sweep, is fast sweep a firmware upgrade?
Yeah, so if you have existing installed base of Keysight or Agilent spectrum analyzers, let's say PXAs, MXAs, EXAs, depending on your hardware configuration and vintage, those can be upgraded.
I'll add just a little bit to that. Fast sweep is a standard feature now in the PXA and the UXA, and then that's the N9030A PXA, the N9040B UXA. It can also be a standard feature in the N9010A EXA or the N9020A MXA if you have one of the following three options: the DP2, which is digital processor 2, it's an IF bandwidth processor, the B40, which is 40 megahertz of analysis bandwidth, or option MPB, microwave preselector bypass. So if you have any one of those three options, you have the necessary hardware, and you can easily update your analyzer to have fast sweep.
Okay, thanks, Pat. So here's another question. Why do the second and third order products cause more problems as compared to other order?
That usually has to do with their magnitude and the fact that typically second and third order have a tendency to, their mixing products have a tendency to mix in band with your actual signal of interest. So together with their magnitude and their tendency to mix in channel, those always end up being the biggest ones you want to chase first.
Okay, thanks, Riyadh. Here's another question. What is the effect of spurs on filtering and isolation?
What are the effects of spurs on filtering? So usually with filtering, the idea of filtering is to actually to minimize those spurs, right? And so if, for example, you choose, depending on your filtering choice, you either choose a slow roll-off filter or a high Q sharp roll-off filter. Both of them have trade-offs in terms of passband response. So if in some cases you want to maintain the group delay signal quality of your transmitter, and so you can't go with a high Q filter. So the trade-off there is if you have spurs that are too close to your filter skirt or inside your channel or on the filter skirt, you end up having a larger spur than you originally planned for potentially, or what your system can tolerate. And so you need to be able to manage and balance the spur selection and the filter attenuation level that's going to be necessary for your end design. And so that gets magnified. So if you have, let's say, a cascaded amplifiers and mixers, if you apply poor filtering at the very early stages of the design, as you ripple through your RF chain, the magnitude of those spurs can actually grow. And so it's very important to actually minimize the spurs at the first stages of your amplifier or filter or whatever chain you're working on, so that it doesn't cascade and ripple through the whole RF. So I don't know if that answered the question, but that's what I do know.
Okay, thanks, Riyadh. I think we have time for one last question. It is there an application that can help someone dynamically calculate probability of intercept or uncertainty budget?
Yes, I believe the AppNote 150, I believe, has some tools for that, where there's also a POI application note that we have that explains how we calculate POI for our spectrum analyzers. That's all inside the slide deck, which will be sent to you afterwards. I highly recommend you review some of those application notes. It goes through great detail on explaining both the POI for real-time spectrum analysis as well as traditional swept analysis.
Okay, thanks, Riyadh. So that is all the time we do have for today, and I'd like to just reiterate that we will be emailing you a link when the on-demand version of this presentation becomes available. Please share it with your coworkers, and we'll also include a copy of the slides. So you will be getting that in a post-event email. Once again, please, if you can, please complete the survey for us. And finally, we'd like to thank you again for joining us, Keysight Technologies, for our webcast, Characterizing Spurious Signals. And this was brought to you once again by Keysight Technologies. Please continue to visit us at www.keysight.com/find/events for upcoming webcasts in the future. Thank you again, and have a great day.